And now with some interesting news regarding quantum gas, we send it over to Brian Kang and Adam Rosenthall, who are with us live from Fishers, Indiana.
We have a pretty interesting story about quantum gas.
Oh, that's right, Brian. Quantum gas defies what was previously thought of the Kelvin scale, and we now know more about it. But does quantum gas defy absolute temperature?
Quantum gas is a sub-zero temperature on the Kelvin scale, practically saying that it's less than no energy, if that makes any sense. But now let's discuss how quantum gas is even possible.
Well, to create a quantum gas, we would want all the particles making up the gas to be indistinguishable. In other words, they have to be the same molecule and same internal state.
Typically, atoms repel, making the configuration stable. But scientists began to use magnetic fields and lasers to adjust the magnetic field so the repelling atoms are now attracted. This adjustment causes the atom to be more stable at a sub-zero temperature than a temperature above zero.
Another necessity would be to control something called the hyperfine state. The hyperfine state is the orientation of the electron spin and the nuclear spin. This nuclear spin inside the atom make up the molecules that form the quantum gas. This must be accounted for, which is why mandating the hyperfine state is very important.
So everything going on inside the nucleus must be lined up, pretty much saying that everything has to be correct in a way. So even the hyperfine state, which is usually considered something to be minor or insignificant, must be carefully fixed for the creation of a quantum gas.
Now, there are a few known properties of quantum gas that have been discovered since the finding of it.
One, for example, is that a cloud of atoms drift upwards and expand against gravity instead of contracting because of gravity.
But tell me, Brian, what makes this property any different?
Because in usual everyday cases, clouds of atoms typically move downwards because of gravity. Gravity is something that causes objects to fall down, pulls objects to the center of the world, which explains why clouds of atoms move downwards. But in the unusual state of quantum gas, these clouds of atoms drift upwards.
There's also another property of quantum gas that might even sound more confusing than everything we have said so far. Technically, quantum gas really isn't colder than absolute zero.
That may seem like a paradox, but Adam is right. Usually on a Celsius and Fahrenheit scale, when there is a temperature below zero and it is negative, then it is absolutely cold and is unbearably freezing. But on a Kelvin scale, a negative temperature is hotter than a positive Kelvin temperature.
You might be asking yourself, why is this even important?
Quantum gas is relevant to us because it clears up all the confusion caused by quantum mechanics. So then, why is quantum mechanics useful?
Quantum mechanics has led to almost all of our technological advances, such as the laser, the Blu-ray player, personal computers, and so much more. But we won't be able to create more original innovations without completely understanding what quantum mechanics is. And quantum gas is just another progressive step to discerning quantum mechanics.
Also, think of all the possibilities if this kind of gas could be produced at a large-scale level. If quantum gas could be produced more widely, it could be both dangerous and helpful to us.
These all could definitely be very helpful outcomes, but quantum gas could also be a big help for cosmologists. This is because quantum gas has similar properties to dark energy, a thing that is mostly unknown, but is believed to be the main force behind the expansion of the universe, a topic that could be further developed.
Let's say know more about this relationship between quantum gas and dark energy because there is more unknown than there is known about both these subjects.
Previously raised the question if quantum gas defies absolute temperature.
It does not defy absolute temperature because absolute temperature is defined as no energy, and no energy means there is no movement. But in a quantum gas, there still is movement, so technically it does not defy absolute temperature.
Gas is a very interesting topic, but there's still so much unknown about it. We've shared some of the basic details about it, and we'll continue to update you as we learn more about quantum gas in the near future.